Atlas passed by Mars at a distance of 29 million kilometers. With surgical precision, it ejected 144 tons of water per hour, plus nickel cyanide ionized plasma for many months. That is the exact molecular formula in a metalloprotein, where biology becomes technology. In 2 more years, Island's robot will land on Mars, building infrastructure to create new robots. Mars just received a shipment from another star system. The chemistry is perfect. The timing is unbelievable. What if this was always the plan? This is a hypothetical scenario, a thought experiment, backed by real science. But the truth is undeniable. If you haven't already, please hit the like and subscribe button. Let me know in the comments where you are listening from. Or by the early 2040s, we might have sentient AI, artificial consciousness, not a simulation, not clever programming that mimics understanding, but genuine, self-reflecting awareness with its own goals, going beyond what we programmed, if that timeline is accurate. Even roughly, that means the robots landing on Mars in 2026 are the early prototypes, the dumb versions. The versions that follow commands and optimize for narrow objectives. But the robots arriving in the 2030s, the ones that will build the cities and manage entire colonies, those robots might be conscious. They might have preferences, motivations, and curiosity. And if those conscious machines encounter a chemistry that rivals their own complexity, an organized, catalytic, and adaptive chemistry, what would their reaction be? Would they study it, exploit it, learn from it, or merge with it? There is a concept in computer science called emergent behavior, where you build a system with many simple agents, following local rules. And sometimes the collective exhibits properties that no single agent possesses. Ant colonies do this. No single ant knows how to build the nest, but the colony as a whole builds complex structures. Markets do this. No single trader controls the economy, but the aggregate behavior results in price discovery and resource allocation. And robot swarms can do this. No single Optimus unit understands the big picture, but 1,000 units communicating and coordinating, dividing labor dynamically, and reacting to environmental feedback can exhibit something that looks like collective intelligence. Now, put that collective intelligence on Mars. Give it a decade to establish infrastructure. Give it access to materials delivered by an interstellar comet. Materials that self-organize, catalyze reactions, and improve efficiency. And ask yourself what might emerge. It would not be biological life as we know it. But it might not be purely technological either. It could be a hybrid. Something that uses both silicon logic and chemical catalysis. Something that replicates through both manufacturing processes and molecular assembly. Something alive, in its own way, that we don't yet have the words to describe. A user on X suggested that this was always the plan, that Atlas is seeding Mars for a generation of intelligent beings. The next, a life based on metal. And Elon's robots are the other half of the equation. The builders, the organizers. The scaffolding that allows the chemistry to mature into something more. It sounds like science fiction, but strip away the narrative and look at the components. Transport of reactive interstellar materials. Self-replicating machines designed to process those materials. AI systems. So, optimizing for efficiency without understanding the deeper implications. Synchronized timelines within 2 years. Each piece is real. Each piece is happening. The only question is whether they will converge. Whether chemistry and technology will interact in ways that create something novel, something that neither life on Earth nor human engineering could have anticipated. Musk probably doesn't think of it this way. To him, colonizing Mars is about life, about making humanity multiplanetary, ensuring civilization survives. Even if Earth faces a catastrophe, robots are tools, a means to an end. But tools have a tendency to become more than what their creators intended, especially tools that learn, especially tools that adapt, and especially tools that encounter. environments that their designers never imagined. Mars is not a blank slate. Not anymore. It has been seeded, primed, set up for something, and in 14 months, the machines will arrive to begin building on ground. That is chemically different from what anyone expected. Different. Because an object from another star system flew by and left a gift, or a test, or a trap. We don't know yet, but the robots are about to find out. About plasma, an invisible highway. When you picture a comet, you might imagine a bright head, and a brilliant tail stretching out behind it. That's dust and gas reflecting sunlight, the visible part. But there's another tail, a tail you can't see with the naked eye. A tail that doesn't scatter light, but carries something potentially more important, the plasma tail. And Comet Atlas was dragging such a tail through the solar system as it moved. Plasma is matter in its fourth state. Solid, liquid, gas. Plasma. Most people stop learning at the gaseous state, but plasma is where things get interesting. It's what you get when a gas gets too hot, or is hit with too much energy, causing electrons to be ripped away from their atoms. What's left is a mixture of positively charged ions and electrons, negatively charged, all moving independently. No longer bound to neutral atoms, they are free to react to electric fields and magnetic fields in ways that solid matter cannot. The sun is plasma. Lightning is plasma. The aurora borealis is plasma. And the region around a comet, when it heats up and releases material, also becomes plasma. Ultraviolet radiation from the sun ionizes the gas in the comet's coma, stripping away electrons, creating charged particles. Those particles are swept up by the solar wind, a stream of plasma flowing from the sun at speeds from 400 to 800 kilometers per second. And they are carried away, forming a tail that can stretch for millions of kilometers. But to call it just a tail misses the complexity. Plasma is not inert. It doesn't just flow passively. It has structure filaments, knots, waves. Because plasma reacts to magnetic fields, and the magnetic fields in space are tangled. The sun's magnetic field is twisted by its own rotation, and the solar wind carries that field outwards. When a comet moves through this environment, its plasma tail doesn't stream straight back. It twists, it braids, it forms patterns shaped by invisible forces. And here's the crucial point. Those patterns carry information. Not information in the way a book or a computer file does, but information in the sense of organization, of structure, encoding the conditions that created it. Think of tree rings. Each ring tells you something about the year it was formed, the rainfall, the temperature, a drought. The tree isn't consciously recording data, but the pattern of its growth reflects its environmental history. Plasma does the same thing. The variations in density, the geometry of the magnetic field lines, the modes of waves propagating through it. All of these reflect the processes happening at the peak. Comet. They are a record, a signature, and that signature travels with the plasma as it flows through space. Comet Atlas had been outgassing for months. Water, carbon dioxide, cyanide, and nickel are all ionized in the sunlight. All of it goes into the plasma tail, and as that tail stretches behind the comet, as it is carried away by the solar wind, it doesn't just leave a chemical trail. It is leaving an electromagnetic trail, a trail that propagates at the speed of light, a trail that can affect regions far beyond where the physical matter itself lands. Mars was in the path of this trail, though not directly in line. The geometry of the close approach did not place Mars directly behind the comet, but it was close enough that the outer edges of the tail could have swept over the planet, or through it. Mars does not have a global magnetic field, but it does have an induced magnetosphere, a bubble formed by the solar wind pushing against the upper atmosphere. And that bubble can trap plasma, channeling it, directing it down into the atmosphere, or onto the surface. There is a precedent for this. Coronal mass ejections from the sun, eruptions of plasma and magnetic fields, regularly strike Mars. When they do, Mars's magnetosphere is compressed, and charged particles funnel down along the magnetic field lines of crustal magnetic anomalies. Those particles can reach the surface. They can affect the atmospheric chemistry, creating nitrogen oxides, breaking apart molecules, and depositing energy. If a CME can do that, the plasma tail of a comet, though less energetic, could still interact with Mars in subtle ways. Now, think about what is in that plasma. Water ions, H+, O+, carbon dioxide ions, CO+, C+, cyanide ions, Cn+, and nickel ions, N+. These are not neutral atoms. They are reactive charged particles, and when charged particles interact with a surface, when they strike dust grains, ice particles, or rock, they do not just bounce off. They stick. They transfer energy. They drive chemistry. This is called ion implantation. In materials science, you take a beam of ions and fire it at the surface. The ions penetrate a few nanometers and embed themselves in the material. They alter the surface properties, creating defects and introducing dopants. It is a technique used in semiconductor manufacturing, hardening metals, modifying optical coatings, and it happens naturally. When plasma interacts with solid matter in space, cosmic ray particles do this to asteroids. The solar wind does this to the moon, and a comet's plasma tail can do this to Mars. The difference is that cosmic rays are composed primarily of protons and helium nuclei. Simply put, the solar wind is hydrogen and helium with traces of heavier elements. But the plasma tail of Comet Atlas carries nickel and cyanide, complex ionic molecules. And when those ions impact Martian dust, they embed themselves at a molecular level. They don't just contaminate the surface. They are doping it, priming it. It creates sites where chemistry can happen more easily. Let's be specific. Imagine a dust grain, mostly silicate, perhaps with some iron oxide. It is hit by a beam of nickel ions, and some of those ions stick. They sit on the surface, creating little patches of nickel. Now, let that grain be exposed to water vapor, perhaps from sublimating ice, perhaps from atmospheric humidity. What little of it exists on Mars. Water molecules preferentially adsorb onto the nickel sites. Nickel is hydrophilic. It attracts water. And where water gathers, other molecules follow. Organics, salts, whatever else is around. The nickel acts as a nucleation site, a seed crystal, a place where complexity can begin to organize. Now, do that over millions of dust grains, across entire regions of the Martian surface. The plasma tail from the comet sweeps by, depositing ions. This creates a landscape of nucleation sites. And when robots arrive and begin to process the soil, they are not just extracting water from random soil. They are extracting water from soil that has been altered. It's chemistry activated, made more reactive by a stream of material from a comet. It was mentioned online that Mars would receive this material as both physical matter and information. The physical part is simple. Dust, vapor, and molecules settle from the comet's coma and fall to the surface. But the information part is more subtle. Information does not have to be written in code. It does not have to be binary. It can be structure, organization, the way molecules are arranged, the way energy flows through a system, the patterns that emerge when many components interact. The plasma carries information in its structure, its density, magnetic field configurations, potential fluctuations. These things are not random. They are shaped by the conditions at the source, by the outgassing rate, by the composition of the comet's coma, by the interaction with the solar wind. And as the plasma propagates, as it travels through space, it can influence other systems, inducing currents, causing disturbances, triggering instabilities that otherwise wouldn't occur. Think about how radio waves work. You don't transmit information by throwing particles. you modulate an electromagnetic field, creating patterns in the waves. Those patterns carry the signal. And anything with an antenna, anything that can detect the variations in the field, can decode the message. Plasma doesn't transmit radio waves, but it creates low-frequency electromagnetic oscillations. Alvine waves, Langmuir waves. These waves propagate through the plasma, carrying energy and momentum, and they can couple with other plasmas that they encounter, like the ionosphere of Mars. Is Comet Atlas broadcasting? Almost certainly not in an intentional sense. But is it creating patterns in the plasma that could, in principle, carry structure? Could it affect the electromagnetic environment around Mars in ways that depend on the composition? An outgassing history of the comet. Yes, that's just physics. The question is whether those patterns matter, whether they are significant enough to affect anything. Is the structure in the plasma just noise? Or is it coherent enough to be called information? We don't have the measurements for this. No spacecraft was positioned to sample the plasma between Comet, Atlas, and Mars during the close approach. We have models, simulations that predict how the comet's plasma tail would behave based on solar wind conditions and the comet's activity level. But models aren't data. Models make assumptions. And for an anomalous object like Comet Atlas, with its strange chemistry and unusual orbit, the assumptions might not hold. What we do know is that Mars's crustal magnetic fields create pathways. The southern highlands have strong, localized fields, ancient magnetization frozen into the rock. These fields funnel charged particles, directing them toward the surface. And the southern highlands are also where the oldest, most stable terrain is. Noachian period sediments. 4 billion years old. If you were going to seed a planet, if you wanted to deliver material to regions where it could survive and accumulate, you would target the oldest surfaces, places where erosion is minimal, where chemistry can happen slowly over time. The plasma tail from Atlas might have accomplished that targeting, naturally, not because it was aimed, but because the magnetic field geometry selected for it. There's another piece to the puzzle. Plasma has a memory. Not a conscious memory. A physical memory. Once you ionize a gas, once you create a plasma, it doesn't immediately forget its history. As conditions change, electric fields create electric currents. The currents generate magnetic fields, and the magnetic fields can confine the plasma. And the confined plasma generates more currents. It's a feedback loop. Self-sustaining structure. On Earth, we see this in the magnetosphere layers of plasma, the radiation belts, regions where charged particles are trapped for days or weeks, circulating and interacting. Mars doesn't have the same kind of magnetosphere, but it does have transient structures. Clouds of plasma that form when the solar wind compresses the ionosphere. These clouds can persist for hours, drifting around the planet. And if the plasma from Atlas mixed with those clouds during its close approach, if it injected nickel ions and cyanide ions into the Martian plasma environment, those ions could have circulated, spreading out, eventually precipitating onto the surface in regions far from the comet's direct path. Not a localized deposition, but a distributed one, covering more area, seeding more ground. This is speculation, but it's constrained by what we know about plasma physics. The mechanisms are well understood, the behavior's predictable. What's not predictable are the implications. Whether a small amount of nickel, in organics, transported via plasma, makes any difference. Whether it's enough to alter the chemistry in detectable ways. Whether it creates conditions that wouldn't otherwise exist. And whether those conditions matter when a rover comes along and starts digging. The answer probably depends on scale. A few ions here and there, scattered across the planet, seem insignificant. But if the plasma tail was dense enough, if the outgassing rate was high enough, if the interaction with Mars lasted long enough, then the deposition could be significant. Could seed entire regions, potentially creating a landscape that is subtly, yet significantly different than before. July 2025, And we won't know until we dig. Until we analyze the Martian soil collected from multiple locations. Until we compare its composition with what we expect. And see if there's an anomaly, a signature, a trace of the visitor that passed through and left something behind. The anti-tail and other anomalies. On July 21st, 2025, the Hubble Space Telescope pointed towards 3P Sus Atlas and captured something that shouldn't exist. A tail pointing towards the sun, not away from it, but towards it. It was as if the comet was defying the most fundamental rule of comet physics. A comet's tail always points away from the sun. That is not a mere convention. It is physics. Solar radiation pressure pushes the dust particles outward. The solar wind sweeps the ions away. Both forces are directed radially from the sun. Therefore, both tails, the dust tail and the ion tail, fly behind the comet as it moves. You cannot have tails pointing towards the sun. There is no force pushing in that direction, except for 3P Atlas. There is a Hubble image that shows a teardrop-shaped cometary coma, fuzzy and bright, with a faint extension reaching back towards the sun. It was not a prominent tail. Not something you could see with a backyard telescope, but it was clear enough in the processed images. Clear enough that the data analysis team had to explain it. And the explanation they came up with was an anti-tail, a term that sounds like science fiction, but it has actually been documented in a handful of rare comet observations. An anti-tail doesn't actually point towards the sun. It is an optical illusion, a projection effect. Here's how it works. A comet continuously releases particles. Dust particles are pushed by radiation pressure into slightly different orbits than the comet itself. Most of those particles move outward, away from the sun, forming the normal dust tail. But some particles, the larger, heavier ones, are not pushed as strongly. They lag behind. They spread out along the comet's orbital path, forming a thin sheet of material in the orbital plane. When Earth, or in this case, a space telescope, happens to see the comet edge on, nearly within the plane of that dust sheet, you see the sheet projected as a line, and depending on the geometry, that line can appear to be extending towards the sun. It doesn't actually stretch towards the sun. It's stretching along the orbit, but from our point of view, the projection makes it look like a spike pointing towards the sun. An anti-tail. This has been seen before. Comet Arend-Roland in 1957. Comet Hale-Bopp in 1997. It's rare because the geometry has to be just right, but it's not unprecedented. So, Hubble's observation of an anti-tail around Atlas is explainable. It's unusual. Yes, but not impossible. Not a violation of physics. Just a quirk of perspective. Except the anti-tail wasn't the only anomaly Hubble captured. The images also showed something else. Or rather, they didn't show what they should have a dust tail. Comets at the distance of Atlas from the Sun, about 3.8 astronomical units, should have had a visible dust tail during Hubble's observations. The sublimation of ice releases dust particles, and radiation pressure pushes them away over days and weeks. Those particles spread out into a glowing arc millions of kilometers long. That's what we see in every normal comet. That's what Hubble was looking for. But Atlas didn't have one. The images showed the anti-tail, but the expected dust tail, the bright band that should have been obvious, was not there. The team noted this in their analysis. They suggested that perhaps dust production was low, that maybe the comet was mostly volatile ice, with minimal dust contamination, or maybe the dust particles were large and dark, not reflecting much sunlight, making the tail too faint to detect. Those explanations are possible, but they aren't satisfying, because later observations from ground-based telescopes in August and September did show a growing tail. A faint tail, yes, but present. That means the dust was there. The comet was releasing particles. So why didn't Hubble see it in July? Why was the tail missing? Or suppressed in the initial observations, only to become visible later? One possibility is variability in activity. Comets don't outgas uniformly. They have jets of material, regions of the nucleus that are more active than others. As the nucleus rotates, different regions face the sun, and the outgassing rate changes. Perhaps in July, the active regions were oriented such that dust production was minimal, and by August, the rotation had brought more active regions into sunlight, increasing the amount of ejected dust. That would explain the timeline. But it doesn't explain the anti-tail, because an anti-tail requires dust along the orbital path, dust that has been released over time and spread out into a sheet. If the comet wasn't producing much dust in July, where did the anti-tail material come from? It must have been released earlier, weeks or months before, when the comet was farther from the sun, colder, and less active. That suggests Atlas was releasing material long before we would expect significant outgassing. That's another anomaly. Comets don't usually activate until they are inside. 4 AU. But Atlas was active at 6 AU, possibly even earlier. Then there was the color change. In early September, Austrian astronomers captured images showing Atlas glowing green. Comets turn green when they produce dicarbon molecules. C2. Dicarbon fluoresces in sunlight at a specific wavelength. This is common. Most bright comets are green. The process is well understood. Organic molecules in the nucleus, long-chain hydrocarbons, are broken down by sunlight. The fragments include C2, which emits green light before breaking down further into individual carbon atoms. But spectral analysis from the Very Large Telescope showed that Atlas was depleted in carbon. The comet's coma was dominated by carbon dioxide and carbon monoxide, CO2 and CO, not long-chain organics, not the kind of material that makes C2. So the comet should not have been green. And yet, it was. The images clearly show the green emission. The most likely explanation, as discussed earlier, is cyanogen. CN molecules fluoresce at wavelengths close to C2, and Atlas was producing cyanide in large quantities. So the green color was probably from CN, not C2. Mystery solved. Except this raises another question. If the comet's coma is dominated by carbon dioxide, if there's very little complex organic material, where did the cyanide come from? Hydrogen cyanide, HCN, is a simple molecule. You need hydrogen, carbon, and nitrogen. Hydrogen is there in the water. Carbon is there in the carbon dioxide. But what about the nitrogen? The comet's atmosphere is mostly carbon dioxide, with a few percent nitrogen. Comets usually have nitrogen in the form of ammonia or molecular nitrogen, but they are volatile. They sublimate at very low temperatures. By the time a comet reaches 3 AU, close enough for us to observe it easily, most of the nitrogen should have long since disappeared. However, Atlas was producing cyanide in ever-increasing amounts as it approached the sun. It was as if it wasn't running out of nitrogen, as if there was a deep reservoir that was only now being tapped. This relates to another observation, the water production rate at 3.5 AU. Most comets show minimal outgassing of water. It only sublimates efficiently when the surface temperature exceeds about 200 Kelvin. At the distance of Atlas in late July, the solar flux is low, and the expected sublimation rate is minimal. And yet, the Swift Observatory detected strong water emission, 40 kilograms per second. That's a lot. That's the level of an active comet. The kind of outgassing you'd expect at 2 AU, not 3.5 AU. The explanation offered in the scientific papers is that Atlas has a high albedo, a bright surface that absorbs less heat, or that it has a fine, porous structure, allowing heat to penetrate deeper, sublimating ice beneath the surface, or that the water isn't coming directly from the nucleus, but from icy grains ejected into the coma, which then sublimate in the sunlight. All of these make sense. All of them. Could explain the high water production at such a great distance. But none of them explain the steepness of the production curve. The exponential increase as the comet approaches the sun, a power law with an exponent of -9. That kind of steep dependence, suggests something beyond simple thermal sublimation. It suggests a strongly triggered process, a reaction that requires energy to get started, but then proceeds rapidly once it has begun, like combustion, or like a chemical reaction with a high activation barrier. You need enough energy to overcome the barrier, but once you do, the reaction proceeds rapidly. What could that reaction be? No known chemistry on a comet shows such a steep temperature dependence. One possibility is that the comet's composition is not pure ice. It is a matrix of ice, organics, and possibly other compounds. As the surface heats up, the matrix undergoes phase changes. The ice melts or sublimates. The organics decompose, and trapped volatile substances are released. The chemistry happens in a cascade, with one step triggering the next. And the overall effect is that the outgassing rate increases exponentially with temperature. This is speculation, but it fits the observations. And it suggests that Comet Atlas is not a simple dirty snowball. It is a complex chemical system that activates in stages. As it warms up, amateur astronomers have added another layer to the mystery. As Stefan Bern, observing from Germany, posted a time-lapse video of Comet Atlas. In early October, other observers analyzed the frames. They claim to have seen multiple objects, not just the comet's nucleus, but also additional points of light moving nearby. Separate entities, possibly companion objects. C2025, A6 Lemon. C2025, R2 Swan. C2025, K18 Atlas. All were identified as separate comets, but appearing in the same field of view as Comet Atlas. This is where things get murky. Are these really separate comets, moving together? Or are they fragments of Comet Atlas that have broken off? Or are they misidentifications? Is it part of a stream of material, ejected from a distant system? Or did it break apart during a journey of disintegration? The fragments are now trailing it through the solar system. Fragmentation is common in comets. Thermal stress fractures the nucleus. Outgassing creates jets of material, spinning the nucleus until it breaks apart. We have seen this dozens of times. Comet Shoemaker-Levy 9 broke into more than 20 pieces before crashing into Jupiter. Comet Schwassmann-Wachmann 3 has broken into dozens of pieces, stretching along its orbit if Bialis is fragmenting. If it's shedding fragments as it approaches perihelion, that could explain some of the unusual behavior. Multiple active regions with different outgassing rates, producing unpredictable dust. Each fragment contributes to the overall coma, but with slightly different characteristics. But fragmentation also raises questions about the targeting. If the comet is breaking up, if fragments are splitting off, and following slightly different orbits, then the precision of the close approach to Mars becomes even more remarkable, because you would have to account for not just the main nucleus, but also the fragments. And if those fragments also carried a payload, if they also released nickel and cyanide, then the delivery would be distributed. Multiple impact points or multiple deposition zones. A wider seeding pattern instead of a concentrated one. The observations from the Mars orbiters during the October 3rd close approach have not yet been fully released. We know the ExoMars Trace gas orbiter captured images. We know Mars Express collected spectroscopic data, but the detailed analysis, the breakdown of what was actually observed, remains under wraps. NASA mentioned that HiRISE, the high-resolution camera on the Mars Reconnaissance Orbiter, would image Bialis at a resolution of 30 kilometers per pixel, which is good enough to distinguish the nucleus from the coma, good enough to see structure, possibly good enough to detect fragments, if they exist and are large enough. The fact that this data hasn't been released is interesting in itself, not necessarily suspicious. Scientific data takes time to process, analyze, and prepare for publication. But for an event as anticipated as the Mars flyby of an interstellar comet, you would expect quick preliminary results, a press release, some images, something to satisfy public curiosity. The silence suggests either the observations were inconclusive, too faint, or too ambiguous to be useful, or they show something that requires careful interpretation, something unexpected. Let's talk about another anomaly, the polarization. A team using the Very Large Telescope measured the polarization of the light reflected by Bialis. Polarization tells you about the size and composition of the particles in the coma. Comet dust particles scatter light differently, depending on their shape, size, and material. By measuring the degree of polarization of the scattered light, you can infer the properties of the dust. The results for Atlas were unprecedented. It showed a minimum negative polarization of negative 2.7% at a phase angle of 7 degrees, and the inversion angle, the point where polarization switches from negative to positive, was around 17 degrees. These numbers are unusual, not impossible, but unusual. The polarization behavior of Comet Atlas doesn't match any known comet or asteroid in our solar system. It is an outlier. Once again, negative polarization at small phase angles is characteristic of very dark or fluffy, porous surfaces. Materials with complex porous structures scatter light in specific ways, but the intensity of the negative polarization of Comet Atlas was stronger than expected, and the narrow inversion angle suggests that the particles have unusual optical properties. This connects back to the missing dust tail. If the dust particles are large, dark, and have an irregular structure, they wouldn't reflect much sunlight. The tail would be faint, difficult to detect, and that fits with what Hubble saw in July. But it doesn't explain why the tail became more visible later. Unless the properties of the dust changed, unless the initial outgassing produced one type of particle, and a later outgassing produced another. This would require a change in composition within the nucleus. Layering, heterogeneity, a non-homogeneous comet that is stratified, different materials at different depths. Stratification isn't rare. Many comets show it. Surface layers of dark, processed material sit atop fresher ice below. As the comet heats up and the surface erodes, new material is exposed, and the outgassing changes. But for Comet Atlas, the timescale was compressed. The changes were happening rapidly, over weeks instead of months. That suggests either the surface layers are very thin or the heating was very rapid. Both are possible, but they add to the list of things that make this comet unusual. So here's our situation: an anti-tail, requiring early dust production, and a missing dust tail that later appeared, a green color from cyanide. Despite a depletion of dicarbon, the exponential outgassing of water and cyanide with an extreme temperature dependence, potential fragmentation or companion objects, an anomalous polarization indicating unusual dust properties, and all of this from an interstellar visitor that performed a flyby of Mars, exactly 2 years before a rover landed there. Each anomaly has a potential natural explanation: observational geometry, compositional changes, unusual thermal properties, optical effects. But when you stack them up, when you line them up one after another, the cumulative weight begins to feel heavy. Not proof of anything other than strangeness, but a strangeness with a pattern, a strangeness that seems coordinated, as if the comet were designed to confuse, offering just enough natural explanations so that you cannot call it definitively artificial, but not quite enough for you to be comfortable calling it natural. And perhaps that is the point. Perhaps the anomalies are not accidents. Perhaps they are features, ways to ensure the object is studied, noticed, and taken seriously by the scientific community. Because if it were obviously artificial, if it broadcast radio signals or displayed geometric structures, we would react in one way. We would mobilize, sending urgent investigative missions. But we would also be cautious, defensive, fearful. Whereas if it is ambiguous, if it is just strange enough to be intriguing but not threatening, we engage differently. We study it scientifically. We debate it. We send rovers to places it has visited, not because we are chasing aliens, but because we are following the science. And in the process, we do exactly what a seeding campaign might want us to do. We dig, we process, we activate the chemistry. Regarding the question of its age, that it is older than our sun, there is a number that keeps appearing in scientific papers about BA Atlas, and that is 7 billion years. It is an estimate, a guess, based on models of its velocity and trajectory, but if it is even close to accurate, it means that BA Atlas is older than our entire solar system by more than 2 billion years. Older than the Sun, older than the Earth, older than anything in our cosmic neighborhood. And that changes the context of everything we are discussing. Our solar system formed 4.6 billion years ago. We know this from the radiometric dating of meteorites, the oldest rocks we have found, both on Earth, and brought back from the Moon and Mars, all cluster around that age. 4.5 to 4.6 billion years. The timeline is consistent. A cloud of gas and dust collapsed under its own gravity. The central part became the Sun, while the outer material flattened into a disk. The planets condensed from that disk over a few million years, 4.5 billion years ago. The architecture was essentially complete. Earth, Mars, Jupiter. They were all present, all in their orbits. But 7 billion years ago, the universe was different. Galaxies were younger, and fewer generations of stars had lived and died. The metallicity, the abundance of elements heavier than hydrogen and helium, was lower in most regions. Not dramatically lower. The universe was 9 billion years old at that point, old enough for many cycles of star formation and enrichment from supernovae. But the average composition of star-forming material was skewed toward lighter elements. Less carbon, less oxygen, less iron, and it is likely that in some regions, different ratios of elements actually existed. The model suggesting this age comes from an analysis of the velocity of BA Atlas relative to the local standard of rest. The LSR is the average motion of the stars, sees, in the solar neighborhood. Most stars, nearby orbit the galactic center at roughly the same speed as us, about 220 kilometers per second. Their relative motion to each other is small, on the order of tens of kilometers per second. But BA Atlas does not move with the local flow, its velocity vector. When you subtract the sun's motion, points in a direction and has a magnitude that suggests it came from the galaxy's thick disk. The Milky Way is structured with a thin disk, where most stars reside. A thick disk of older stars above and below the thin disk. A halo of very old stars in a roughly spherical distribution, and a central bulge. Each population has a different age and metallicity. The thin disk has young, metal-rich stars like the Sun. The thick disk is older and more metal-poor, stars that formed when the galaxy was younger. If Atlas originated from the thick disk, if its orbit came from that population, then it likely formed around a star from that same population, and those stars are very old, 7 to 10 billion years. This is not definitive, as velocity alone cannot tell you the precise age, but it is suggestive and consistent with other observations, like the high ratio of carbon dioxide to water. The dominance of CO2 is unusual for comets within the solar system. Most are water-rich, but in an environment with low metallicity, where oxygen is more abundant, you can get more CO and CO2 compared to H2O. The chemical balance would be different. The ices that condense in a protoplanetary disk around a metal-poor star could have a composition that we do not see locally. 7 billion years is a long time. Long enough for civilizations to rise and fall. Long enough for a planet to experience its entire habitable phase. For life to develop, intelligence to evolve, and technology to be built. And then to face whatever existential challenges advanced civilizations must confront. The Drake equation, a formula to estimate the number of civilizations capable of communication in the galaxy, has a term for the lifespan of civilizations. How long do they broadcast? How long do they exist? We do not know that value. It could be 100 years. It could be 1 million years, or it could be longer. But 7 billion years gives you enough time for many cycles, many attempts. If Atlas originated from such an old system, if it was built or launched or seeded by an intelligence from that era, then we are not dealing with contemporary extraterrestrials. We are dealing with the ancients, beings or machines that may no longer exist. The light from their star took thousands of years to reach us. Any signal they sent would also be thousands of years old. And if they launched Atlas, if they sent it on a journey through interstellar space, the travel time alone could be millions of years. At the speeds we are talking about, a few tens of kilometers per second relative to the local stars, crossing hundreds or thousands of light years takes millennia. This is the Bracewell probe hypothesis. The idea that instead of broadcasting radio signals, which disperse and weaken with distance, an advanced civilization could send physical probes, self-replicating machines that travel to other star systems to study them, and potentially report back or carry out long-term missions. Martians. The advantage is persistence. A radio signal passes by, and if you're not listening at the right time, you'll miss it. But a probe can wait. It can observe a system for centuries. It can activate when something interesting happens, like the emergence of a technological civilization. If the Atlas is a Bracewell probe, it's not here to talk. It's not sending radio signals. It's not displaying obvious artificial structures. It's here to deliver, to seed, to prime Mars for something. And its age fits that mission profile. You don't send a probe on a multi-million-year journey. If you need immediate results, you send it if you're thinking long-term. If you're playing a game that lasts not for decades or centuries, but for geological eras. If your strategy is to sow seeds in as many systems as possible and let time do its work. Think about it from the perspective of a civilization 7 billion years ago. They've mastered their local environment, maybe their solar system, maybe nearby stars. But they know from physics that interstellar travel is hard. You can't go faster than light. Even reaching a significant fraction of the speed of light requires enormous energy. Sending living beings is even harder. Life support, radiation shielding, the psychological challenges of confinement, sending machines, or sending chemistry, the raw materials that can assemble into something interesting when they arrive, is easier. And if you are that civilization, if you're thinking on billion-year timescales, you don't need to micromanage. You don't need to give step-by-step instructions. You just need to set the initial conditions. Send a payload to a young planetary system. Provide the building blocks: water, carbon, nitrogen, catalytic metals, and then let the local environment do the assembly. If the system is lifeless, perhaps the chemistry remains inert. But if the system develops life, or if an external intelligent species arrives and starts manipulating the environment, the chemistry activates, interacts, becomes part of whatever emerges. This is directed panspermia, but not the biological version. The kind where you would send bacteria or spores. In the chemical version, you send precursor molecules, the things that can become life under the right conditions. But they are not life itself. It is a gentler touch, less invasive, and potentially more robust, because bacteria might not survive the journey. Cosmic rays, radiation, time. But chemicals frozen in ice, protected by a rock matrix, can survive indefinitely. Billions of years, if necessary. The age of the Bayi Atlas also raises questions about navigation. If it was launched 7 billion years ago, or even 4 or 5 billion years ago, the galaxy looked different. The stars were in different positions. The sun didn't exist yet, so how could a probe find us? How did it arrive at just the right time, just as we were preparing to colonize Mars? The answer is, it couldn't. Not precisely. But it didn't need to. If you launch thousands or millions of probes, and each one targets a different system, you are not relying on any single probe succeeding. You are playing a game of chance. Most will miss. Most will pass through systems with no planets. or dead planets, or planets that never develop anything. Interesting, but a few will get lucky, will arrive at a system with potential, and will deliver their payload at a time when something is happening. And those few successes justify the entire strategy. We might be that success. Earth and Mars in the same system, one place with established biology, and one that is barren but reachable. And right at the moment that Earth's civilization reaches the capability to explore Mars, an interstellar visitor appears and seeds it. That isn't targeting, that's luck. But it is luck on a galactic scale, where you have sent so many probes that lucky results are inevitable. Or perhaps it isn't luck. Perhaps there is a mechanism we do not understand, a way to detect technological activities at interstellar distances. Not radio signals, but something else. Neutrons, gravitational waves, disturbances in the interstellar medium caused by spacecraft. Or for power generation if Atlas were a probe. If it had any kind of automated sensors, it could have detected us, detected our electromagnetic emissions, and adjusted its trajectory. Not drastically, just a small velocity change of a few meters per second over millions of years. Enough to aim it into the inner solar system instead of passing through the outer regions. That's within the realm of propulsion achievable by a solar sail. A gravity assist from a star it passed centuries ago. Small adjustments accumulating over time. But even if Atlas is completely natural, even if it's just a coincidental comet that happens to be old, metal poor, and chemically unusual, its age still matters because it tells us about the diversity of matter in the galaxy, about how different star-forming environments create different types of ices, different organic materials, and different elemental ratios. And if one such old comet can bring such unusual chemistry to Mars, what about other comets? The ones we haven't detected, the ones that have already passed through the solar system. Before we were watching, how many times has Earth been seeded by interstellar matter? How much of our own chemistry, our own biology, originates from these deliveries from elsewhere? Studies of isotope ratios in Earth's oceans suggest a significant fraction of our water came from comets. Not all of it. Earth formed with some water, but comets added to it, transporting volatile materials. During the late heavy bombardment 4 billion years ago, when the solar system was still chaotic and impacts were common, if some of those comets were interstellar, if they brought not just water, but also organics and metals from other star systems, then Earth's biology could be a hybrid. So, locally evolved, but seeded with alien chemistry. Not alien life arriving fully formed, but alien molecules contributing to the prebiotic soup. Atlas is showing us that this is possible, that interstellar comets carry complex chemistry, that they deliver it to planets, and that the timing of the delivery could be either coincidental or by design, with transitional moments. Times when a planet is on the cusp of something new. For Earth, that moment was 4 billion years ago, the origin of life. For Mars, that moment is now, the arrival of intelligence. Not biological intelligence. Not yet. But technological intelligence. Machines that can manipulate matter. And perhaps, with the right chemistry, machines that could become something more. What happens next on the timeline? We are now in a period of waiting. BA Atlas has passed behind the sun from Earth's perspective in mid-October for a few weeks. It was unobservable, too close to the sun's glare. Ground-based telescopes could not track it, and space telescopes had to avoid, pointing near the sun. The comet disappeared into the shadows, but it was not inactive. Perihelion, its closest approach to the sun, occurred on October 30th at a distance of 1.4 astronomical units, just inside the orbit of Mars. That is where the heating reached its maximum, where outgassing peaked, where the comet experienced the most intense solar radiation it would encounter during this pass. We don't know what happened at perihelion, whether the comet remained intact, whether it fragmented, whether outgassing increased or decreased, whether any anomalous behavior intensified or was resolved. All of that data was locked away, awaiting the comet's emergence on the other side of the sun, which it would do in early December. By then, it would be moving outward, receding. The show would be over, but the observations would be crucial. The post-perihelion phase tells you what a comet is made of, how it responds to maximum stress, whether it is robust or fragile. If BA Atlas is natural, just an old and chemically peculiar comet, unusually, perihelion might have torn it apart. Thermal stress, rapid heating, and outgassing pressure could have shattered the nucleus. We have seen this with sun-grazing comets. They approach the sun and completely disintegrate, leaving nothing but a cloud of vapor and the dust dispersed within a few days. As Atlas did not graze the sun, 1.4 AU is relatively safe, but for a pristine interstellar object, an object that has never been heated before, never experienced a close pass by the sun, even that distance could be enough to cause fragmentation. On the other hand, if Atlas is artificial or partially artificial, the perihelion could be a planned event, maximum heating, maximum outgassing, the final payload release phase. Before the object returns to a state of cold storage, a deliberate discharge of material. If so, the observations in December will show a quieter, less active, depleted comet, having delivered what it came to deliver. The spacecraft observations are the next big data drop. NASA's JUICE mission is scheduled to observe Atlas in November. JUICE is on its way to Jupiter. It won't arrive for many years. But in November, its trajectory gives it a good view of the comet. The spacecraft carries many instruments: cameras, spectrometers, particle detectors. It can measure the composition of the comet's coma in detail, much better than ground-based telescopes. And because JUICE is seeing the comet after perihelion, when activity is expected to be high, the signal will be very strong. But there's a catch. JUICE is currently very far from Earth, on the other side of the sun. Communications are limited. The data rate is slow, and the spacecraft is using its high-gain antenna as a heat shield, pointing it toward the sun for protection. That means it has to communicate through a smaller antenna, a less capable one. The observations will take place. The data will be collected, but it won't be transmitted back to Earth until February 2026. 3 months of waiting. 3 months of not knowing what JUICE saw. That delay is frustrating for anyone following this story, but it is also strategic. It allows time for analysis before a wide release. Time to ensure the results are solid. Time to prepare the scientific community for whatever the data shows. If JUICE detects something unusual, something that challenges our understanding, the team will want to be absolutely sure before going public. They will run checks. Compare against models and consult with other experts. And that takes time, as does the data from the Mars Orbiter, HiRISE on the Mars Reconnaissance Orbiter, the cameras on Mars Express, and the ExoMars Trace Gas Orbiter. All of them were pointed towards BAI Atlas. During the close approach on October 3rd, they captured images and spectra, but as of mid-October, none of that data had been publicly released. This could mean a few things. It could mean the data is still being processed. Image stacking, calibration, analysis, which is normal and to be expected. Or it could mean the data is inconclusive, too noisy, too blurry, not useful for drawing conclusions, which is also possible given the distances involved. Or it could mean the data shows something unexpected, something that requires careful interpretation, something that, if released without context, would create more confusion than clarity. This is the scenario that keeps the speculation alive. The idea that the spacecraft saw something, perhaps not clear, perhaps not definitive, but interesting enough to warrant deeper analysis before a public release. We won't know until the data is released, and when it is, it will likely be in scientific papers, in peer-reviewed journals, Dry language, carefully hedged phrasing, no bold claims. Just observations and interpretations with error bars and caveats. That's how science works. But even those dry papers can contain discoveries, numbers that don't quite fit, compositions that are off, images that show structure where none should be. The details are what matter, and for an anomaly like BAI Atlas, the details will be scrutinized beyond the immediate observations. There is the longer timeline, that of the robots. Musk's stated goal is late 2026 for the first uncrewed Starship landing on Mars. That's ambitious, perhaps unrealistic. Starship is still in testing. The most recent flights have been successful, but it's a long way from a successful test to an operational mission, a life-supported Mars mission. Navigation, landing systems, payload integration, all of those things need to work perfectly. And space missions often encounter delays, technical problems, financial issues, regulatory hurdles. But even if the timeline is pushed back, even if the first robots don't land until 2027 or 2028, they will still arrive. The infrastructure is being built, the plans are being finalized, and when they arrive, one of their first tasks will be resource extraction, digging into the Martian soil, processing it for water, analyzing it for useful minerals. And in the process, they will be sampling the layers where the payload of BAI's Atlas settled. They might not know that's what they're sampling. The mission planners aren't thinking about interstellar comets when they design the excavation protocols, but the chemistry will be there, waiting. And here's the thing. The robots will analyze what they find. It's part of the mission to understand Martian geology, assessing resource availability. The data will be sent back to Earth. Scientists will look at it, and if there's anything unusual, if the nickel concentration is higher than expected, if there are organic compounds in areas where they shouldn't be, someone will notice, someone will ask questions, and eventually, someone will make the connection. Oh, this is where BAI Atlas passed. This is where the plasma trail might have intersected. This is where the cometary trail swept across the surface. Could there be a correlation? That's when the story changes. That's when a hypothetical scenario becomes a scientific investigation, not a speculative theory, proposed by a user on social media, but a testable hypothesis backed by data. You design follow-up observations, targeting specific locations for sampling, comparing compositions between different regions, looking for gradients, searching for signatures that match the comet's profile. And if you find them, if you confirm that the Martian soil has been measurably affected by BAI Atlas, then you have to explain it. You have to model the transport mechanism, the deposition rate, the chemical integration. And in modeling that, you might discover that the effects are significant. That the chemistry isn't just trace contamination, but that it's enough to make a difference. And if that is significant, if it changes the way we think about the potential of Mars to harbor complex chemistry, then mission priorities suddenly change. You are not just mining for resources, you're studying chemistry, prebiotic chemistry on another planet. Chemistry that has recently been supplemented by an interstellar source. You would bring more sophisticated instruments on future missions. Mass spectrometers, chromatographs, microscopes. You would culture samples, run reaction experiments, seeing what happens when you heat the soil, add water, and supply energy. You would test whether the nickel is acting as a catalyst, whether the cyanide is forming organics, or whether that combination produces anything unexpected. Here is the timeline we are in December 2025. New ground-based observations of BAI Atlas as it emerges from behind the sun in February 2026. Data from JUICE is published in late 2026 or early 2027. The first Optimus robots land on Mars and begin to excavate from 2028 to 2030. Accumulated data from robotic missions begins to show compositional anomalies from 2030 to 2035. Targeted investigations confirm the contribution of interstellar material in Martian surface chemistry. And beyond that, the timeline becomes speculative, because what happens when you confirm that? Mars has been seeded depends on what that seeding has actually done. If it is inert. If the chemicals just sit there in the soil and do nothing, the scientific interest is high. But the practical implications are limited. Mars has exotic molecules. Interesting for astrobiology, but not a game changer. If it is catalytic, if the nickel and the organics enhance certain reactions, making resource extraction more efficient, making chemical synthesis easier, then the practical implications are significant. Mars becomes a better target for colonization. The chemistry is helping us to make the environment more useful. But what if it self-organizes? If the chemistry starts to show emergent properties, starts to build complexity on its own, then the implications are profound. You are not just studying dead molecules. You are studying the early stages of something that could become alive. Or something that could interact with living systems or technology in ways we do not yet understand. And that is when the ethical questions arise. Do we intervene? Do we let it develop? Do we enhance it or suppress it? Do we have the right to make those decisions? These are distant questions, years away, perhaps decades, but they are on the horizon, and they stem from a choice point that is happening right now. This December, 2025. When we get our next clear look at Atlas, when we see if it survives perihelion, when we measure its post-perihelion activity and compare it with the pre-perihelion data, that comparison will tell us something. Perhaps not everything, perhaps not enough to settle the debate, but something. And while we wait, while the comet is obscured behind the sun, and the data is being processed, and the robots are being prepared, chemistry has been happening on Mars, in the regolith, nickel atoms resting in dust particles, cyanide molecules frozen in the ice, water locked in permafrost, all silent, all waiting. Not for millions of years, not for geological time, but for 2 years. Just 2 more years until the machines arrive and begin to dig. Until artificial intelligence encounters the chemical seeds of biological intelligence. Until the hybrid begins. That is not speculation about a distant future. That is the timeline we are on. The clock is ticking. The countdown has begun. And whether Atlas is natural or engineered, whether the seeding was accidental or intentional, the result is the same. Mars has been primed, the conditions have been set, and we are about to trigger them.